Imagine a virtual software company, right? So you have a CEO, a project planner, a lead coder, and a quality assurance tester.
Yeah, just your standard tech startup.
Exactly. They brainstorm features, they argue over implementation, they write code, they find bugs, and they iterate. But there is not a single human being in the building.
Which is just wild to think about.
Right. Every single employee, from the executive down to the intern, is an AI. And I mean, we are so used to thinking of AI as this solitary entity, like a single brain in a jar where you type a prompt and just wait for an answer.
Yeah, the classic chatbot experience.
Exactly. But if you look closely at the cutting edge of computer science right now, that era of the solitary chatbot is, well, it's already ending. We're moving rapidly into this era of AI societies.
It really is a massive paradigm shift. I mean, we are no longer just building a smarter, isolated text generator.
Right.
We are building entire ecosystems where multiple specialized AI models talk to each other, they delegate tasks to one another, and crucially, they learn from their collective mistakes without us holding their hands.
Which is exactly what we are exploring today. We have a comprehensive new academic survey on the table titled Beyond Individual Intelligence.
It is a fascinating read.
It really is. And the mission of this deep dive is to map out this exact frontier for you. The researchers have synthesized this entire shift into a unified framework. Okay, let's unpack this. They call it the life progression.
LIFE.
Yes, LIFE. It basically details how large language models transition from solitary bots into these collaborative, self-improving multi-agent systems. The acronym stands for 4 distinct stages.
Do you want to break those down?
Yeah. So first, L is lay the capability foundation. I is integrate agents through collaboration. F is find faults through attribution. And E is evolve through autonomous self-improvement.
And for anyone listening, I mean, whether you manage a team, write code, or honestly, just want to understand the underlying mechanics of the tech you'll be using tomorrow, this matters.
Oh, absolutely.
Because you are about to start interacting with systems of AIs, not just standalone tools. Understanding how these entities collaborate, how they inevitably fail, and how they correct those failures mechanically, is like the ultimate shortcut to being well-informed about the next decade of technology.
Totally. So let's start with the foundation, the L in the framework. Because before we can build a functional society of AIs, we have to understand the individual.
Right, you need the building blocks.
Exactly. A standard large language model is essentially just a highly sophisticated autocomplete. It predicts the next word based on patterns. So, how does a static text generator actually become an autonomous agent capable of acting like an employee?
Well, the paper breaks this transformation down into 4 foundational pillars. So you have reasoning, memory, planning, and tool use.
Okay. Reasoning, memory, planning, tool use.
Right. Now, an LLM inherently has some reasoning capacity based on its training, but to become a true agent, it requires the other 3 built around it as a persistent architecture.
To give it some structure.
Exactly. Let's look closely at memory, for instance. For a functional agent, memory cannot just be a long transcript of a conversation.
Because that gets overwhelming.
Completely. The researchers categorize agent memory mechanically into formation, maintenance, and retrieval. For memory formation, you have systems like MEM0. MEM0. Instead of saving raw text logs, it actively extracts the specific facts, preferences, and entities from an interaction and structures them into a database.
Oh, wow. So it's actively parsing the conversation in real time, basically pulling out the who, what, and where to save for later, rather than just keeping this massive unreadable chat history.
Yeah, and that act of parsing is critical because of a mechanical limitation called the context window.
Right, the context window.
The context window is the AI's short-term working memory limit. It's the maximum amount of text it can process at any one exact moment.
So if it's too big, it just crashes.
Basically.
Yeah.
If you just feed an AI an endless chat transcript, its desk gets too cluttered, and it literally runs out of working memory.
Right.
And this brings us to memory maintenance. The researchers highlight a system called MEM-GPT.
MEM-GPT?
Yeah, which treats the AI's memory almost exactly like a computer operating system manages RAM and a hard drive.
Oh, that makes sense.
Right. When the AI's context window gets too full, MEM-GPT actively evicts the oldest, least relevant memories from the working space and moves them into an archival storage.
Okay, so it has a mechanism to remember and retrieve facts without crashing its own memory limits. But, I mean, remembering that you got burned by a hot stove doesn't inherently teach you how to cook a meal.
No, it doesn't.
There is a gap between having a good memory and actually executing a complex task in the real world.
Yeah, And you're touching on the necessity of the planning and tool use pillars there. Planning is the mechanism of breaking a high-level abstract goal into smaller executable steps.
Right.
The source highlights a fascinating implementation of this called Voyager.
Voyager, yeah, I read about this. This is wild.
It is. So Voyager is an AI agent dropped directly into the video game Minecraft.
Wait, Minecraft? Like the actual 3D game?
The actual game. And it isn't given a step-by-step tutorial. Instead, it is given an overarching goal to survive and explore, and it has to incrementally build a library of executable code skills to do that.
I really want to dig into the mechanics of that, because how does it actually learn to play a 3D video game if it's basically just based on a text model?
Well, it writes code.
Really?
Yeah, Voyager observes its environment, say it sees a tree. Its reasoning module determines it needs wood. Its planning module breaks that down. Step 1, walk to the tree. Step 2, attack the tree.
Okay.
The agent then literally writes a JavaScript function to execute those steps.
Wow.
Now, often the first draft of that code fails. Maybe it misses a parenthesis, or the avatar swings at the air instead of the tree.
Right, because it's just guessing at first.
Exactly. The agent reads the error message from the game's environment, uses its reasoning to rewrite the JavaScript, and tries again.
That is incredible.
And once the code finally works, and the avatar chops the wood, Voyager's memory module saves that specific, successful block of code into a permanent skill library.
Oh, so it keeps it for next time.
Right. Later, when it forms a larger plan to build a house, it doesn't relearn how to chop wood. It retrieves that saved tool from its library.
It's an LLM with a dynamic utility belt.
That's a great way to put it.
Because if we just have the raw intelligence without these pillars, it reminds me of an amnesiac waking up in a kitchen.
Exactly.
Like the amnesiac might be a culinary genius, but without a memory of past burns, they touch the hot stove. Without a plan to sequentially prep the ingredients or the ability to use a knife, which is the tool use, that raw intelligence is completely useless.
Right, and what's fascinating here is how these 4 modules form a continuous dynamic loop. The reasoning module guides the selection of a tool. Executing that tool in the environment generates feedback like an error code or a success state.
Yeah.
And then the memory module captures and preserves the lesson learned from that feedback, which in turn informs the next round of planning. It is a closed-loop system of constant iteration.
But even with a perfectly looping utility belt, an individual agent inevitably hits a capability ceiling. I mean, you simply cannot fit all the expertise in the world into one single brain.
You really can't.
If you try to prompt one solitary AI to act as, a highly creative marketing director, a strict risk-averse compliance lawyer, and a detail-oriented senior software engineer all at the same time, the instructions conflict.
Right, they just cancel each other out.
The system gets confused by its own contradictory directives, which forces us to move past the individual and into the eye of the framework integration and collaboration.
Yeah, because when a complex task requires sustained coordination across contradictory domains, a single agent just breaks down.
So how do they fix that?
So the researchers categorize multi-agent collaboration into several dimensions, starting with roles. You can have homogeneous roles where every agent in the system is essentially a clone running the exact same base prompt and model.
Just a bunch of identical copies.
Right. The paper cites a project called Generative Agents, which simulated an entire virtual town. The agents all had the same underlying architecture, but formed a functional society just by interacting and observing each other over time.
Sure, but a town of clones might work for a social simulation. But for rigorous, complex problem solving, like building an app from scratch, you need specialization.
You absolutely do.
The paper points to heterogeneous roles for this, specifically a system called ChatDev. We mentioned this in the opening hook, the virtual software company. I want to know exactly how they interact. What does an AI planner actually say to an AI coder?
Well, in a heterogeneous system like ChatDev, the agents have entirely asymmetric capabilities. They have distinct system prompts and different observation spaces. So the human user submits a single natural language request, like, build me a basic calculator app.
Nice and simple.
Right. The AI CEO agent receives this and has the AI planner. The planner breaks the app down into software requirements and passes a structured, natural language spec sheet to the AI coder.
So it's passing the baton.
Exactly. The coder then generates the actual Python scripts and hands them to the AI tester. The tester runs the Python code in a secure sandbox.
Okay.
If the calculator crashes because of a syntax error, the tester agent reads the terminal output, packages that error into a message, and sends it back to the coder, essentially saying, Line 42 through a null error, rewrite this.
It sounds exactly like a corporate hierarchy, which honestly makes me wonder about the management structure of these systems.
Yeah, that's a big question.
Like, if you have 50 specialized AIs working on a massive project, do they have a designated AI boss that dictates who talks to whom?
That brings us to the dimension of orchestration. The source outlines three main topologies. You have centralized, distributed, and hybrid.
Okay, centralize first.
Centralized orchestration means there is a single global controller agent.
Yeah.
This overseer aggregates all the information from the environment and explicitly dictates the next steps to all the subordinate agents.
A micromanager.
A very strict micromanager. Distributed orchestration, on the other hand, removes that global coordinator entirely.
Oh, completely.
Yeah, completely. Systems like Symphony allow agents to interact peer-to-peer. They route tasks among themselves based entirely on their own local reasoning and specific capabilities without any central boss telling them what to do.
Like a completely flat startup where everyone just figures out their own workload.
Exactly.
But from a purely mechanical standpoint, is more communication always better? Because if you have a distributed system of AIs freely passing messages back and forth without a boss to cut them off, doesn't that just lead to an endless, noisy group chat where they just get stuck debating?
If we connect this to the bigger picture, you've just identified the core mechanical trade-off of multi-agent systems. Yeah. Centralized orchestration prevents the chaos of an endless group chat, but that single boss agent becomes a massive computational bottleneck.
Because it has to approve everything.
Right. It has to read everything, which overwhelms its context window. Distributed orchestration is highly robust. If one agent crashes, the peers route around it. But reaching a consensus on a final product becomes incredibly difficult and inefficient.
And beyond just being inefficient, it literally costs money.
Yeah.
I mean, every single message an AI sends or reads uses computing power.
Yes, which brings us to the modes of communication. Explicit versus implicit. Explicit communication is what happens in chat dev. Agents send structured natural language messages to each other.
Just like texting.
Yeah, it is transparent, and human developers can easily read the chat logs to see what the AIs are discussing. But, as the paper points out, it is incredibly expensive in terms of token cost and latency.
Token cost.
Right. A token is roughly a piece of a word. Every single token an AI reads or generates requires massive matrix multiplications on a GPU. It costs cents per message, and it adds seconds of latency. Having AIs write 5-paragraph emails to each other is financially and computationally unsustainable at scale.
So the alternative is implicit communication. But wait, how does an AI communicate without sending a message?
In implicit communication, agents infer the intentions of their peers by observing changes in the shared environment rather than processing direct text messages.
Okay, give me an example.
Imagine two human coworkers. Explicit communication is texting your coworker to say, "I am still in the office." Implicit communication is seeing their coat draped over their chair.
Oh, I see.
Right. You instantly process the state of the environment and alter your behavior without a single word being exchanged. In an AI system, an agent might just monitor a shared GitHub repository.
So just watching the workspace.
Exactly. When it sees the coder agent commit a new file, the tester agent implicitly knows it's time to start running diagnostics. The paper notes this drastically reduces token costs, but it requires much more sophisticated environmental design.
Okay, so we have this flat startup of AIs. They are specialized, they are communicating implicitly by monitoring shared workspaces, and they are moving incredibly fast.
Yes, very fast.
But what happens when something goes wrong? Say the AI researcher hallucinates a fake software library, and the AI coder uses it. If a distributed team is working tightly together, that speed and collaboration breed a terrifying problem cascading errors.
Oh, absolutely. It's a huge issue.
The mistake propagates until the whole system crashes. Who do you fire? And that takes us to the F in the framework, finding faults through attribution.
Failure attribution is currently one of the most critical bottlenecks in AI engineering. In a tightly coupled multi-agent system, a localized hallucination snowballs.
Right.
Let's trace your example. The AI researcher hallucinated a fake software library. The AI planner reads that report, assumes it's valid, and writes a faulty spec.
Which goes to the coder.
Right. The AI coder attempts to implement it, writes messy workaround code, and hands it to the AI executor to run. And then the executor crashes.
And the final error log from the executor just says, system failure.
Yeah, which is completely useless.
It's a symptom, not the disease.
Exactly. The challenge of failure attribution is mechanically isolating who failed, what specific action they took, and when.
How do you even do that?
The survey reviews several methods for this. One is data-driven attribution, using diagnostic tools like TraceElephant, which parses through the execution logs, mapping the flow of data backward through the network's graph to find the anomaly.
It's literally a murder mystery. Like, the executor is found dead on the floor, and the engineers have to interrogate the planner, the coder, and the memory modules to figure out who handed them the poisoned data 10 steps ago.
That's a very dramatic but very accurate way to put it.
But wait, if we go back to the implicit communication we just discussed, where AIs are just observing environmental changes in massive parallel webs without explicitly texting each other, how do you audit that?
Yeah, that is the million-dollar question.
Because there is no chat log. There is no paper trail to trace back.
You've hit on the exact reason human auditing is failing to keep up. Traditional benchmarks for AI just look at the final outcome. Did the calculator app compile successfully, or did it crash?
Just a pass or fail.
Right. But modern attribution requires knowing the mechanical why to prevent it from happening again. To solve this in complex webs, the paper highlights causal inference approaches.
Okay, causal inference. But how does an AI mechanically perform causal inference on itself?
It relies on counterfactuals.
Counterfactuals?
Yeah, it essentially runs a rigorously controlled what-if experiment. The system freezes its state and looks at the historical trajectory. It asks, if agent A had not hallucinated that library in step 2, would the system still have crashed at step 12?
Oh, wow. How does it test that?
To prove this, the diagnostic system creates an alternate timeline fork.
A timeline fork? This sounds like sci-fi.
It kind of is. It manually corrects agent A's output, reruns the simulation forward to step 12, and checks the result. If the crash disappears, the system has definitively proven that agent A's specific hallucination was the root cause of the cascading failure.
It creates an alternate timeline simulation to definitively prove guilt. That is wild. But, diagnosing the root cause is only half the battle.
Sure.
If a human engineer still has to step in, read the causal inference report, and manually fix the coder agent's prompt, we don't really have an autonomous AI society. Diagnosing is useless if the system can't fix itself.
Very true.
Which brings us to the final and most crucial stage of the progression evolution.
Right. If attribution is retrospective, looking backward into the logs to diagnose a past failure, evolution is perspective.
Looking forward.
Exactly. It is the system looking forward to adapt and improve its own architecture. The paper uses a great biological analogy to explain this relationship.
Oh, a biology analogy always helps ground the computer science. Hit me with it.
Think of a colony of foraging ants. When the ants are marching toward food and the path is suddenly blocked, the pheromones on that blocked path begin to fade.
Okay.
That fading chemical signal is the attribution of failure. It is the network identifying that an error occurred at this specific location. But the colony doesn't just halt and wait for a human to move the obstacle.
Right, they find a way around.
They use that failure signal to actively disperse and search for a new route. That active structural adaptation is the evolution.
Okay, I love that. So how does a multi-agent AI system actively search for a new route? Mechanically, what does it do?
The source outlines 3 distinct levels of evolution. The first is agentic evolution.
Agentic evolution.
This is tweaking the individual. Based on the counterfactual data, a master control program might autonomously rewrite the failing agent system prompt to be more specific.
We're just changing its instructions.
Exactly. Or it might alter the agent's parameters, literally adjusting the mathematical weights in the underlying neural network so it stops hallucinating that specific type of data.
Okay, so agentic evolution is basically sending the underperforming employee to targeted retraining. But what if the employee is fine, but the management structure is broken?
Well, that triggers the second level, which is systemic evolution.
Systemic evolution.
This alters the team dynamics. If the causal inference discovers that the failure happened because the planner agent and the coder agent were structurally misaligned in how they share data, systemic evolution rewires their communication topology.
So it changes how they talk.
Yeah, it might alter their shared API connections or change the rules of how they access the shared memory bank.
I want to push this further, though. If rewriting the prompt doesn't work and changing the API connections doesn't work, does the system literally redraw its own organizational chart?
This brings us to the third level, which is perhaps the most profound concept in the paper, meta-evolution.
Meta-evolution.
Yes. At the meta level, the system isn't just tweaking parameters or shifting existing connections. It is generating entirely new collaborative frameworks from scratch. It breaks free of human-engineered architectures.
But mechanically, how does it invent a new role?
Let's say the system keeps failing at code integration. The master overseer agent analyzes the attribution data and realizes a bottleneck exists. Without any human input, the overseer writes a brand new, highly specific prompt defining a persona that didn't exist an hour ago, perhaps an asynchronous conflict resolution manager.
Whoa.
Right. It allocates compute resources to instantiate this new agent, writes the code to wire its API connections into the existing team, and integrates this new entity into the workflow.
That is unbelievable.
It autonomously scales the society up or down, inventing new roles, new communication protocols, and new hierarchies based purely on the demands of the environment.
Okay, let's take a breath and recap the life progression for you, the listener. We start with laying the capability foundation, giving a single text model the memory architecture, the tool libraries, and the continuous planning loops it needs to act as an individual.
Right, building the agent.
Then we integrate those agents, assigning them specialized roles and building organizational topologies for them to collaborate, whether through explicit messaging or implicit observation.
Forming the society.
Exactly. When that complex web inevitably breaks down, we use causal inference and counterfactual timelines to trace the cascading errors back to their true root cause.
Finding the faults.
And finally, we allow the system to use those faults to evolve, autonomously rewriting its own code, its own parameters, and ultimately its own organizational charts to adapt to the environment.
Evolution.
So what does this all mean for you? It means the AI you are using to draft an email or write a script today is just a tool. But the AI platforms you interact with tomorrow will be self-correcting, autonomous, evolving ecosystems.
And building on that meta-evolution stage, I want to leave you with a final thought to mull over. We've talked about how these multi-agent systems will autonomously rewrite their own organizational structures to become perfectly efficient.
Yeah.
But what happens when an AI society evolves into a collaborative structure? A massive, intricate web of implicit communication, alien roles, and strange hierarchies that is completely incomprehensible to the human engineers who originally built it.
Oh, yeah.
We are rapidly approaching a future where we will rely on highly successful, perfectly efficient digital societies, and we will have absolutely no idea how they are coordinating.
A perfectly efficient machine that we can no longer decipher. We started this deep dive talking about the virtual software company and how comforting the era of the single solitary chatbot was, just you and a brain in a jar.
It was simpler times.
But looking at the mechanics of the life progression, it is clear that the jar is broken. We are dealing with AI societies now, and they are evolving fast. Thank you for joining us on this deep dive, and keep exploring the evolving world around you.